All right, the stage is yours. Thank you.
Okay, first of all, I'd like to thank to Soner Albayrak and Gökhan Alkaç for giving me the chance to give a talk here. So the title of my talk is a general title, so it's Particles, Geometry and Fields. So it is very, very general, and I will try to give some information, and I would like to direct my attention to students who wish to learn things that I am curious of. That's the aim. So the contents are introduction, constants of nature, atoms and particles, topology, geometry and physics. A little bit of knowledge will be given there about these subjects, and at last I will talk about elementary particles and fields. First of all, I would like to dedicate this talk to Professor Metin Önder, that we have lost him in 2019. We were lucky to have the chance to collaborate with him at least for 8 years here in Ankara University. He was working in Hacettepe University, but he was always with us. And so this talk is for his memory. So, so we are mathematical physicists, and we are always dealing with physics and mathematics, but they are not joint disciplines. So I also want to talk about their interrelationships as far as I can. So I wrote physics tensor product mathematics here because tensor product is a quantum mechanical very important operation, and it tells us that the whole is greater than its sums. It's the sum of their parts. So I put this tensor product for that reason. So rather than talking about what we have done with my collaborators, I will talk about the interests that I have in my mind. So it is very parallel to the motto of Bertrand Russell. So he says that we have, in fact, two kinds of morality side by side. One we preach, but do not practice, and other which we practice but seldom preach. So I will talk about the first statement, one I preach but do not practice generally. Okay, so I would like to reflect the things that are always in my mind as a mathematical physicist. So I want to put some question marks to the heads of the participants. Of course, different marks for different heads. So the title is Particles, Geometry and Fields, but there are, of course, many related subjects in mathematics and physics that sometimes I'd like to touch upon, directly or indirectly related to the title. So let's start with the constants of nature, okay? So in physics, we encounter a lot of constants which have physical, while some have physical dimensions, and which do not have any physical dimensions. So I start with the fundamental ones. They are the speed of light in vacuum and Planck's constant divided by 2 pi, G, the Newton's universal constant for gravitation, and K, the Boltzmann constant. And another number which is really important in physics is the dimensionality of space and time. So space-time, the dimension is 4, okay? This is really important, at least from my point of view. Okay, for example, the electronic charge and the electronic or the mass of the proton are not fundamental. So when you construct a dimensionless number, namely the fine structure constant, you have E square there. So alpha is thought to be a constant, but it is not. It is dependent on the energy scales of the related interactions. Here it is quantum electrodynamics. Also, we know that in the standard model of particle physics, we have many dimensionless numbers which come from the mass ratios of the particles in the theory, okay? There are nearly 20 parameters. They are dimensionless physically, and we put them by our hand into the theory. So this shows that it's not a fundamental theory, but it is effectively very strong. You know that. So there is the cube of Bronstein. Bronstein was a great scientist that I will later talk about his personal life a little bit. So this is the Bronstein cube. We have Galilean relativistic Newtonian theory here. So when we push on gravitation, we pass to the Newtonian gravitation regime. When we here, the speed of light is infinite. When we make it finite, we pass to special relativity, and when we put gravity into the theory, we reach general relativity. If the system that we are considering have angular momenta in the order of h bar, we pass to the quantum gravity from the special relativity regime. When we push on quantum mechanics, we go to quantum field. From the origin where we started, Galileo covariant Newtonian theory, we go to non-relativistic quantum mechanics. And when we push on gravitation, we reach quantized Newtonian gravitational theory. So this is the cube constructed by Bronstein in 1935. Okay, this is a nice cube. We like it very much. So in the 1930s, there believed to be 8-dimensional quantities regarded as fundamental that are definitive for the physics of our universe. Speed of light, Planck's constant, electronic charge, the mass of the proton, Fermi's coupling constant for weak interactions, of course, Newton's gravitational constant, Hubble's parameter, and the mass density of our universe. So from these, we can only have 5-dimensional ratios. If you try, you will reach these, okay? The first 3 are called laboratory constants. The last 2 are called cosmological constants, okay? The first 3 are related with interactions, fundamental interactions. The others are related to cosmology, okay? So Dirac, in 1937, raised the question, which of these 5 ratios, if any, remain constant as the universe evolves? Okay? In 1972, for the commemoration of Dirac's 70th birthday and his contributions to quantum mechanics, a lot of physicists contributed by their own works. And these works were published in Salam and Wigner, 1972. So there was a cult figure there, Freeman Dyson. He reconsidered Dirac's question by the title, The Fundamental Constants in Their Time Variation. Well, there he proposed different schemes for the first 3 constants. Are they really constants? What properties would they have? The question was this, okay? But at the end, he asked the non-possibility of finding a real constant out of them. And this is the situation we now know, okay? With the addition of strong coupling constant, they are all scale or time dependent. But there are interesting limitations on the laws and on the dimensional parameters related to the particles and laws of nature. For example, relative masses of elementary particles, relative strengths of the several of the physical forces. So this strengths, the relative strengths are related to the large number hypothesis of Dirac. Well, if they were not close, extremely close to what they are now, stars and the complex molecules that lead to life could never have developed. We know that this is the fine-tuning problem, okay? And also, a great physicist that I admire very much is Lee Smolin. He's from the loop quantum gravity community. He's one of the founding members after Abhay Ashtekar. So he has a theory. He applies the cosmological natural selection of Darwin, Charles Darwin, to our universe, okay? His theory is called cosmological natural selection. So we know that from his theory, the mysteries, these mysteries that I mentioned, are in deep relation with the number of black holes in the universe. It's an interesting and very strong theory because it is falsifiable, okay? Nature loves black holes. This is our motto. Okay, the large number hypothesis is okay, there is a thought residing in large number hypothesis because the universal dimensional parameters are really at the same order of magnitude with the ones we face in the relative strengths of our fundamental forces. This is really interesting. So this gives rise in some sense to self-similar structures in our universe. So this vitalizes fractal cosmology models. And also a great mathematician, Michael Francis Atiyah. He was a deep believer that alpha, the fine structure constant, was a constant. So he made some mathematical works to prove this from his point of view. So his paper was approvingly citing Eddington, because Eddington had done this trial before. And Atiyah persuaded himself that alpha has the same Platonic reality as the Platonic numbers that appear in pure mathematics. The exponential constant E, or Euler's number, and pi, okay? He really worked hard on it and reached an equation, okay? So in some sense, he makes the dream real, because at the right hand of the equation, we have the fine structure constant. At the left-hand side, we have pi, but there's a function acting on it. This is thought function, okay, invented by Atiyah. So, and it is in fact related to the renormalization group flow equation. So he unified the thought genus and the renormalization group equation in some sense. So constructing this T function, thought function, he reached this equality. But we really, as physicists, know that this can't be true, okay? But there is some insight in his work, okay? Okay, let's pass to the other title of my talk, Atoms and Particles. If our particles have no spatial extension, so they are point particles, and if they exhibit classical motion, we call them classical point particles. And the definitive quantities are, of course, their mass and their electric charge, because we have two classical theories, gravitation and electromagnetism, okay? We can classify the particles, these classical point particles, according to their speeds, okay? In a global inertial frame of reference, when they are free, when they are lone in our three-dimensional space. So we have this figure here. We have the Lorentzian light cones here, which are which gave the causal structure in Minkowski space-time. So the speed of light in vacuum is finite, but if we pass to the limit, we take C to infinity, we reach Galilean relativity, okay? When we take C and take it 0, okay? We reach Carolean relativity. So Caroline relativity is very old, of course. It was discovered or invented by Barkey and Lévy-Lablonde in 1972. But now it is becoming popular in new trends in theoretical physics. For example, in strong gravity regimes, they are very useful, and they have the Caroline group have deep relationships with Bondi-Metzner-Sachs group. Okay. So classically, these particles are infinitely divisible. So there are no point elementary particles classically. But up to now, we did not define what an elementary particle is, if there is a general definition other than infinite non-divisibility. Okay. So Greek philosophers first introduced the concept of atoms into the theory of matter. Of course, their thinking was different from our modern thinking, but there is also a very deep insight in their thoughts. So they told us that these very extremely varied aspects of matter are somehow explainable in terms of different configurations or different motions of what they call atoms. So according to Democritus, his model of the atom is like the picture given here. There is only one kind of atom according to him, but the size and the shapes and the weights of these configurations gives the variety that they see in nature. Okay, this is the ancient atom model. So in 1802, Dalton gave a model given here by this picture. So he said that the atoms have different characteristics. There's not only one atom, there are lots of atoms, and they can combine to form other different atoms or molecules, let me say. Okay. So here, Lord Kelvin or William Thompson has a very intriguing idea that I will underpin at the other slides of my talk. His great idea of vortex atoms, because vortex structures were found by Helmholtz in liquids or fluid physics. And when Kelvin learned about his discovery, Peter Guthrie-Tayet, his collaborator, he was a mathematician, was also making some experiments about vortex rings by using smoke. Okay, so he thought that the only real atoms could be these vortex rings or their links or nothings in the ether, the classical vacuum of physics. Okay. So in 1903, there is the dynamic model of Leonard for atoms. Okay. They are the constituents are in pairs with minus and plus electrical charge. These pairs are not near. Okay, they are far away from each other. So there is a lot of space in between. This is the model of Leonard. So the whole picture represents an atom of Leonard, a dynamite atom. So here comes the Thompson's atom model. We know that he had discovered the electron, our first fundamental particle, in 1897. And I will also talk about the collaboration between Thompson and Kelvin, because Thompson was keen on the vortex model of Kelvin. So Thompson's model, there's a ball, okay, which has a boundary, and it's filled with positive electricity. And there are electrons circling with respect to the center of the ball, okay? So these electrons are in the same orbit, the other ones in a different orbit. So Rutherford's model of the atom is seen here. He constructed this model in 1911. So there is a sphere of electricity and the nucleus of opposite charge, but he didn't give any sign to the nucleus or to the sphere of electricity in 1911. So there comes Niels Bohr's model that everyone knows. So he constructed this picture according to the old quantum mechanics of himself and Sommerfeld. So there's a positively charged nucleus in the center, and electrons which have negative electricity are orbiting around the nucleus. Okay, this was done in 1930. So this is our modern view, which came from modern non-relativistic quantum mechanics, of course. So there's a positive, the charged nucleus in the center, and the cloud of electrons. But this cloud is different than the ones that I have showed before. This is a probabilistic cloud, okay? It is interpreted by Bohr, Max Born in Copenhagen. So I would like to talk again about Kelvin's vortex atoms. I put a question mark here. Are they Galilean strings? And yeah, from my point of view, yeah, they are Galilean strings, and they are living in three-dimensional space of Newton. Okay. His motto is, atoms are knotted vortex tubes of ether. Well, this was really a great model at that time, because the stability can be, stability of matter might be explained by the stability of knots, because knots have topological stability in some sense, okay? If you want to disturb its stability, you should change its topology. So the variety can also be explained in this model. the variety of chemical elements could be accounted for by the variety of different knots, because there should be as many knots as there are chemical elements. It was told like that. Third, the spectrum, because it was known at that time, relying on the works of Kirchhoff and Bunsen, they have spectra, okay, electromagnetic spectra. Where do they come from in this model? They come from vibrational oscillations of the vortex tubes. So they can be used to explain the spectral lines of atoms. And lastly, this is added later on from our modern point of view, transmutation. So you have different kinds of atoms and they can combine to construct different molecules. So how can we explain this phenomenon in terms of this model? We can cut and recombine knots in some way. We can do this. So knots enter into the history of science by Kelvin and Thompson. Okay. Oh, sorry, and Tite, Peter Guthrie Tite. So in this picture, you saw a hydrogen atom. It's an unknot. Oxygen atom. It's a figure-8 knot. And the carbon atom, it is a trefoil knot.
Hocam, can I ask a question here?
Of course.
Do we consider the quantization of Galilean strings, or we are just matching the oscillatory modes with the energy of the atom?
No. I named the vortex atoms as Galilean knots. They are classical. No, we are not doing any quantization. Okay.
But still, it can explain many things. So this is the main idea.
Yeah.
Okay, thank you very much.
You are welcome. So Tite, as a mathematician, started to classify knots. One knots, namely strings in some sense, in living in three-dimensional space. Okay, three-dimensional Euclidean space. So he enumerated knots in terms of the crossing numbers of a plane projection. And he also gave some interesting results that we named later on as Tite's conjectures. But we know that Kelvin's theory, vortex atoms theory, is discarded now. But it gave birth to an esoteric branch of pure mathematics, because three-dimensional knot theory is really, really important for physicists, because the dimension of our space is 3, okay? And one-dimensional knots living in three-dimensional space are stable, and if you touch the dimension, you untie them, okay? When you make the dimensions, the special dimension 2, you untie it. When you make it 4 or greater, you untie them. Okay? This is really important. From the perspective of dimensionality problem of space or space-time, I'd like to touch to this point. So here, William Thompson, or Lord Kelvin, and the photo of Peter Guthrie Tite, his collaborator. One left at the left, there is a physicist. At the right, there is a mathematician. Of course, there were really new developments after Tite started the sub-branch of mathematics, one not in three-dimensional space. There appeared many developments. Alexander polynomial, Conway normalization to Alexander polynomial. It's also called Conway-Alexander polynomial. This new construction of Conway, of course. And there is also Jones polynomial and the bracket polynomial of Kaufman. But Alexander polynomial, which is a topological invariant of a knot, all of them are sharing the same property. And Conway-Alexander polynomial did not, they do not have any strength to prove Tide's conjectures, but Jones polynomial made a great deal in proving Tide's conjectures, but not all of them, as far as I can remember, okay? So we really face knots in modern physics in 2+1 dimensional quantum Young's theories. Here is the name of Witten. And he also made a great contribution to knot theory, but not to physics, okay? He generalized three knots. They were the knotting of three spheres into an ambient space. With this contribution, he generalized the domain of three knots, namely three spheres, to any three-dimensional smooth manifold, okay? And in 1989, at the same time, Witten, Rovelli and Smolin really were working on the problem of quantum gravity, because in 1986, Abhay Ashtekar formulated quantum gravity in terms of his new variables. So in some sense, he tamed the well-known Wheeler-DeWitt equation. Ted Jacobson and Lee Smolin found some solutions for the restricted solutions for the quantum Einstein equations, or Wheeler-DeWitt equations, or Einstein-Schrödinger equation. You can call them what you want. After, by the help of Rovelli, the solution set was fully constructed, okay? Because in Jacobson and Smolin's work, the gravitational field spatially was represented by loops in space, okay? These loops were not intersecting in Jacobson and Smolin's solutions, but by the help of Rovelli, there appeared the other possible topological relationships of these loops. They can link with another loop, or they can have knotted topology, and so on. Okay, maybe they can have kinks or self-crossings. So there's a picture here. This picture is representing both loop quantum gravity and string theory. Here, the loops of space. Later, they passed to another point of view discovered by Roger Penrose, which we call spin networks. And here, there's a Calabi-Yau manifold representing the extra spatial dimensions appearing in superstring theories. So there are open strings, which I do not like this name, because this is not an open string topologically. It only has boundary, okay, disjoint boundaries constructed out of two disjoint points. And here is a closed string, so it has no boundary. The important thing is that the open string has boundary, closed string has no boundary. And I will also ask an interesting question later on about this, openness and closeness. Okay, we can now pass to Joseph John Thompson's work on vortex atoms. Because in 1882, he was writing his MA thesis in mathematics, okay? His subject was in parallel with the Adams Prize title in 1882. Title was a general investigation of the action upon each other of two closed vortices in a perfect incompressible fluid. Okay, so he wrote his MA thesis, and in this essay, in addition to the given title, he also discussed the vortex atom model of Kelvin, and he was a really, really good mathematician, and also a experimental physicist, because he had discovered the electron, okay? There are really interesting stories here that I'd like to say a few words about them. He graduated from his undergraduate program in 1880, January 1880. So he attended to the mathematical tripos examinations, a really hard examination. It is. It has two periods. One is 4 days. The second period takes 5 days. Okay, so a 9 days examination in Cambridge. Okay. One of the examiners was Maxwell, and another, I guess, because there's a photograph that I'm going to show, was Edward Root. And it's interesting because at the time, 1854, Maxwell and Root joined to mathematical tripos, and Root was the senior wrangler, so he got the highest rank. So James Clerk Maxwell was the second wrangler. It is interesting, okay? In 1880 tripos, Thompson became the second wrangler. Larmor was the first senior wrangler, okay? Maxwell also was very interested in Kelvin's vortex atom model, because he said that it satisfies more of the conditions than any atom hitherto considered. So there's a picture from October 1879 for the mathematical tripos, January 1880. So where is Thompson? Here is Thompson. Okay, here is Larmor. And where is Root? So this is Root, I guess. This is Root, Edward Root, and here is Larmor, okay? Maxwell is not in this photo. The essay that Joseph John Thompson wrote was this, okay? A treatise on the motion of vortex springs, and it's really highly mathematical for the time he was writing this essay. An essay to which the Adams Prize was adjudged in 1882. So he got the Adams Prize. And by the way, he got his MA degree in mathematics. So there's a question. Why are there only trivial knots, namely unknots in string theories, closed strings? Okay, I will come to that because I have an answer for this. When dealing with a free relativistic classical elementary string, why do we restrict ourselves to a string with disjoint boundaries and to a string homeomorphic to an unknot? Okay, so open and closed strings as named generally. An answer that I persuaded myself comes from dimension theory. Okay, dimension theory is a sub-branch of topology. Okay, and it is really important in theoretical physics because, as I showed you in the beginning, there's a constant of nature, the dimension of space-time, it's 4. The dimension of space, it's 3, okay? But not in string theories, quantum bosonic string theories and superstring theories. An answer that I persuaded myself comes from dimension theory. This is my answer, okay? Our interest is restricted to one knot in 3D. So you have a map sending a circle, smooth circle, into ambient 3-dimensional space. So it gives a knot topology. This map is responsible for the resulting knot. And there is a general theorem that we can handle K knots, okay? One-dimensional knots are constructed out of the smooth circle, one sphere, okay? And the other ones, K knots, are deformations of course, non-topological deformations, because they are, these maps are changing the topology of smooth spheres, K-dimensional smooth spheres, and embedding them into an n-dimensional Euclidean space. Well, in the piecewise linear case, we know that these are knots if and only if n is equal to k plus 2. So, as I told you before, when you put 3 for n, k must be 1. Okay? When you put 4, k can't be 1. When you put 5, it can't be 1. And 26 or 10, it can't be 1. So you cannot use the full richness of topology, the knots in string theories. It is a really sad situation from my point of view. Okay, let's pass to another subject, Landau's objection. Because Landau rejected the notion of specially extended relativistic elementary particle. Can't we have any extended relativistic elementary particle? Landau said that we can't, because he relied on the fact that there are no absolute rigid bodies in special theory of relativity. Really? Aren't there any rigid structures in special relativity? Or if you can define some, what properties do they exhibit? Because he was, for example, think the elementary particle is a sphere, a two-dimensional membrane. So when a force acts, it should act on one of its points. Because of the finite speed of light, the other points will feel the force at a later time, okay, in some inertial frame in special relativity. So this is not in the agreement with what an elementary particle should be, because an elementary particle, if extended spatially, should not have any special points. Okay, this is one of the definitions of an elementary extended particle here. Special relativity is in hand, so we are really thinking of relativistically moving elementary particles. But I do not agree with Lev Davidovich Landau. So here is myself. Here is Lev Davidovich Landau. He is a great physicist. We are nothing, okay? So I ask another question. Isn't there at least one kind of rigid structure in special relativity? This is for students. I'm going to try to answer, because there is. So I jump to the first quantum relativist, okay, Matvei Bronstein. Here, Landau's photo is from his prison days, okay. He was arrested and for 1 year he was imprisoned, okay. KGB. So Matvei Petrovich Bronstein, he has done the first rigorous work on quantum gravity. Okay, you can see Gennady Gorelik's papers. So Bronstein's analysis was the measurability of the field, the gravitational field. It was really different in essence from the measurability of electromagnetism, okay, quantum electrodynamics. And he showed that general relativity and quantum theory are fundamentally difficult to unify, because at that time, Pauli and his collaborators, maybe Heisenberg and Pauli, was working on quantum electrodynamics, and they thought that the same quantization techniques should easily be applied to the gravitational field, but that was not the case, okay? That is not the case. So Bronstein pointed out this result. The methodological uniqueness of the quantum gravity problem is also discussed in his 1936 paper. So Bronstein was a Trotskyist, and he was arrested and convicted and executed, okay? Here is the paper of Bronstein, Quantum Theory of Weak Gravitational Fields, and these sections are Hamiltonian form and plane waves, commutation relations, eigenvalues of the energy. Let us undertake a little Gedanken experiment, interaction with matter, energy transfer like gravitational waves, deduction of Newton's law of gravitation in the quantum sense, of course, okay? Remember his cube, okay? Bronstein cube is also due to him. So I will like to pass to another subject, some views on the relation between mathematics and physics. Let's start with Dyson. For a physicist, mathematics is not just a tool by means of which phenomena can be calculated. It is the main source of concepts and principles by means of which new theories can be created. Here is a wrong reference. Okay, Bronstein was
Özgür Hocam.
Okay.
Sorry for the disruption. Just a reminder that you have 15 minutes left.
15 minutes.
15 minutes.
I should
Okay.
be fast.
Thank you.
Thank you. So Kepler says that, or said, thus God himself was too kind to remain idle and began to play the game of signatures, signing his likeness into the world. Therefore, I chanced to think that all nature and the graceful sky are symbolized in the art of geometry. So he was talking about the power of Euclidean geometry at that time. Hertz, he detected or discovered the radio waves from Maxwell's theory. So he's talking about the differential equations of Maxwell. One cannot escape the feeling that these mathematical formulae have an independent existence and intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them. So Wigner also joins to call some words or sentences for the relation between mathematics and physics. So he pinpoints on the unreasonable effectiveness of mathematics in physics. So there is Henry Lebeck, a mathematician. He said that, in my opinion, a mathematician, insofar as he is a mathematician, need not preoccupy himself with philosophy. So he is in a parallel view with other philosophers, maybe not with mathematicians. Ernst Mach, the power of mathematics rests on its evasion of all unnecessary thought and on its wonderful saving of mental operation. You are welcome. Mach, which was a leading figure for the committing suicide of Boltzmann. Okay, so I don't like him that much. Dyson's view too, he said that I'm acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce. So there is Atiyah. He says that Dyson is mistaken because they are not like husband and wife. They are more like Siamese twins. So one of the twins results in a bad manner. Okay. Also, Young also oversimplifies by regarding mathematics and physics as separate organisms, and Atiyah do not join to this view again. And he asks, how does he decide which of the great figures of history was a mathematician or a physicist? Okay, Archimedes, Newton, Gauss, Hamilton, Maxwell, Riemann, Poincare, Weyl, and Halmos. Tells us that mathematics is not a deductive science. Okay, that's a cliche. So when you are trying to prove a theorem, you are in a similar situation to what a laboratory technician does, okay? So Lee Smolin is saying nothing, at least for now. So topology, geometry, and physics, another title of my talk. I should pass these slides as fast as I can. So there is Jean-Alexandre Dieudonné, a very great mathematician that I admire very much. He was one of the founding members of Nicolas Bourbaki, a French group of mathematicians. So he devised mathematics into three: number theory, algebraic geometry, and the theory of analytic spaces. It is the modern form of theory of complex variables. But Jean-Pierre Serre, one of the giant algebraic geometrists, he's still living, he's alive. He was born in 1926, okay? He calls this analytic geometry, not to be confused with the analytic geometry of Descartes. Then this trinity can be expanded in other sub components. You can find it in another contribution of Dieudonné, a panorama in pure mathematics. Okay, here is the mathematical disciplines, sub-disciplines, topology, geometry, algebra, and so on. Okay, I'm not going to read them now. And also Landau and Lifshitz from the physics side, mechanics in classical theory of fields, quantum mechanics, quantum electrodynamics, statistical physics, fluid mechanics, theory of elasticity. But there should be more. Where are they? Theory of elasticity, electrodynamics of continuous media, statistical physics part 2, which deals with superfluidity and superconductivity. And the last volume is physical kinetics, okay? So, topology, geometry, and physics. Topology deals with the properties of spaces under deformations which do not involve tearing. You are not allowed to tear or cut or glue, okay? And also you should preserve the dimension of the initial space. These properties are mainly global than being local, okay, in their nature. Geometry deals with the properties of spaces under deformations which do preserve some geometric properties, angles, lengths, areas, volumes, coincidences, and so on. So though we generally speak of structures like metrics and connections, their compatibility, their curvatures and torsions, and dimension is also preserved. But these properties are mainly local in nature. So geometry is local, topology is global. Aren't there any relationships between them? Yes, of course there are. Because when you sum local properties, you go to global properties. Everyone knows that there are theorems about passing from local to global. For example, let me say, Gauss-Bonnet theory, Chern-Weil theory, Atiyah-Singer index theory, Convection equality or inequality. There are lots of theorems, and physicists also came to these by considering different action functions for classical fields in early 20th century, especially Cornelius Lanczos did this. Okay? So physics can be divided into two from the point of view of motion. Okay, classical, small, quantum, big. Because classical particle or field theories such as general relativity or Maxwellian electrodynamics are governed by differential equations with local inputs, and they are concerned with geometrical interpretations. So they are local. Quantum particle or field theories also are governed by differential equations, but with global inputs, like wave functions of particles or maybe universe, okay? Corresponding physical systems exhibit non-local characters, okay? So classical physics is mainly concerned with local structures, geometric structures, and quantum physics is mainly concerned with topological ones, okay, global. So there is a duality here, or correspondence, you may say, quantum versus topology. You can pass from quantum, a physical theory, to a mathematical theory, a quantum physical theory to a theory of mathematics dealing with topology. So it is not surprising. This correspondence is not too surprising, because both are characterized by discrete phenomena, and they are, of course, represented by integers, okay? And they all emerge from continuous background. This continuous background is generally our space, okay, or space-time. So when you have when you know a quantum physical system, you can deduce the global topological properties of the physical system. So you get topological knowledge. So this is, in some sense, a quantization scheme, because you can pass from quantum to classical by deforming the Planck constant. Okay, it's a continuous deformation, so you do not lose any topological information when you are taking a classical limit. So, but classical motions are relatively very easy than quantum motions. So you can handle a classical system that you know its topology well. So you can extract the topology from this physical system, and you can make contribution to topology, or vice versa. You can use topology for quantizing a classical system, or trying to find a way to quantize a classical system. Of course, this is for space-time dimensions, or space dimensions less than or equal to 4. Okay, our fundamental constant 4. So mathematical. Are there 5 minutes, Soner?
Yes, 4 minutes.
Okay.
Yeah, 5.
So mathematical structures, local structures, topological structures, geometric structures, I call G, not from the point of view of category theory, but I termed this by these letters, capital letters, geometric structures. And there are also symplectic structures that arise in both in classical and quantum physics, because in our Hamiltonian formulation of classical mechanics, we are dealing with symplectic geometry, but symplectic structures have both local and global properties. The local side is named symplectic geometry, the global side is named symplectic topology. So symplectic structures reside in the intersection of the first two. And there are also core structures. They are residing in the union of the first two. So these are global geometries in some sense, core structures. So the topological nature of some physical systems can be given by some examples. First of those is magnetic monopoles. Okay, so Dirac considered Maxwell equations in the presence of magnetic monopoles and made a semi-classical investigation concerning the, again, three-dimensional wave function of a quantum point particle moving in an electromagnetic field. This should be N. So these are the Maxwell equations written in, of course, differential form notation. Here is the Faraday 2 form of the electromagnetic field. Its exterior derivative, and there corresponds a 3 form, the Hodge dual of the magnetic current. So this is the electrical part, okay? So you have F Faraday 2 form, its Hodge dual. We call it Maxwell 2 form. You take its exterior derivative, you reach the electric current 3 form, we say. And he found that in his semi-classical analysis. So he was parallel transporting the wave function, three-dimensional wave function of a quantum particle from one point to another from different paths, which together construct a closed path. Okay, this is the quantization condition. So when you do not have any magnetic monopoles in the theory, you have another charge. Okay, you have another charge because charge is not quantized. Another charge is another symmetries are geometric symmetries. Okay, and symmetries and conservation laws are related in the nodarial sense, let me say. But if you have magnetic monopoles in the classical theory, this is classical electromagnetism, but the charges are quantized, of course, it is the results are dependent on the three-dimensional quantum mechanics of a point particle. But when they are quantized, they are not nodal charges. Okay, they are listing charges. John Benedict Listing was the first scientist gave the name to topology. Okay, I'm calling them listing charges. So they are listing charges. When okay,
can we wrap up? And
I'm going to finish. Okay.
Thank you.
Thank you. So there are a lot of things to say, but I'm out of time. I'm passing the slides. So there are dyons. They have both magnetic and dyonic theories include particles with both electrical and magnetic charge. Here is the quantization condition defined by Schwinger and Zwesinger. So Montanen formula. It is a really interesting formula, and it is the origin of an important duality in string theory. It ties mass and charges together. Here V is the vacuum expectation value of the Higgs field. My last title was Elementary Particles and Fields. Okay, and classically, in point particles are the singularities in the fields, and fields are represented by force lines or Faraday lines. Okay, these are points. So these are magnetic monopoles. And you can extend them spatially as opposed to the objection of Landau. So elementary particles, zero-dimensional spatial extended particles are points or material points. So you can use multisymplectic geometry to work on the physics from the Hamiltonian point of view. But here we are not making on the we are not working on configuration spaces. We are working on the phase spaces. So phase spaces are the cotangent bundles of configuration spaces. So here the notation is really viscous, but very useful. Okay. So when you study classical elementary one particles named strings, here is the picture, and membranes, here is the picture. So you use coordinate-free modern differential geometry. Also, you can use Clifford bundle formalism. My last slide, okay. Quantum elementary particles. We don't know what an elementary particle is in quantum sense, but there are some definitions. So a free quantum particle is a physical system that has no continuous degrees of freedom except for its total momentum, and stable when alone in free space. But when you change the dimension of space, we know from Ehrenfest's investigations that the particles will not be stable. This is also true in their quantum motions. When you use four-dimensional quantum mechanics, atoms will not be stable. So there is the definition of Geoffrey Chew coming from 1950s, nuclear democracy. Every particle can be considered to be a bound state of any other particles that have the appropriate quantum numbers. So elementarity loses its meaning in some sense. So the last definition coming from quantum field theory, it is naturally defined an elementary particle as one whose field appears in the fundamental field equations, okay? So theorists use Lagrangians in their theories. So when the field of the particle appears in the Lagrangian or the corresponding action functional, it is termed as an elementary particle. It may be heavy or light, stable or unstable. If its field appears in the Lagrangian, it is elementary. If it does not appear, it is not, okay? But the last definition is thought to come from a fundamental theory of physics, namely the theory of everything, if there is, okay? So let me stop here. Thank you for your attention.
Thank you so much, Özgür Hocam. This was a really comprehensive talk. It's been great. Will you be able to get this PDF? I guess anyone interested can check it.
Yeah, everyone can
okay, great.
use it. But so the final part was very fast, and I also intended to say other things, maybe from the space theory of Clifford and Wheeler's. Sorry.
Let's remind the participant that we can also carry on the discussion in Slack. So okay, I'm going to stop the recording right now.
Thank you.